In this video, I will explain concept of voltage controlled oscillator. Voltage controlled oscillator. A voltage controlled oscillator is an oscillator circuit in which the frequency of oscillations can be controlled by an external applied voltage. This is input voltage, output waveforms. Two types of waveforms are generated: triangular waveform and square waveform. The frequency of oscillations can be controlled by an externally applied voltage. That is called as voltage controlled oscillator. A voltage controlled oscillator VCO is an oscillator circuit in which the frequency of oscillations can be controlled by an externally applied voltage. By an externally applied voltage. This is the definition. VCO provides the relationship between the applied voltage and oscillation frequency. Next important point is the VCO provides the linear relation. Linear is very, very important. Linear relationship between the applied voltage and the oscillation frequency. Applied voltage is called as control voltage. Applied voltage is called as control voltage. This is another important point. Generally, VCO in an oscillator circuit which is used to generate two types of waveforms, square waveform and triangular waveform simultaneously. The frequency of oscillations can be controlled by an external applied voltage. The external applied voltage is called as control voltage. The VCO also provides the linear relationship between the applied voltage and oscillation frequency. The applied voltage is called as control voltage. The control of frequency, with the help of control voltage, is also called a voltage to frequency conversion. Important point. Next point. The control of frequency. With the help of control voltage. Is also called voltage to frequency conversion. Is also called voltage to frequency conversion. This one is another important point here is hence the also called voltage to frequency converter. Another name VCO is also called as is also called as voltage to frequency converter. Frequency converter. Typically, VCO is used to produce square and triangular waveforms whose frequency is controlled by control voltage. Generally, practically, VCO is used to produce square and triangular waveforms. Whose frequency is controlled, whose frequency is controlled by control voltage. Controlled by controlled voltage. This one is these are some important points. The applications of that VCO is frequency modulation, tone generators, and frequency shift keying, where the frequency needs to be controlled by means of an input voltage is called as VCO. Applications, coming to applications, generally frequency modulation, tone generators, and frequency shift keyings. Frequency modulation, FM, Next come tone generators, and the frequency shift keying, where the frequency needs to be controlled by means of an input voltage. Okay? Input voltage called control voltage. Now all the points, frequency of oscillations are controlled by the externally applied voltage. That is the main theme behind this VCO, voltage controlled oscillator. Now, practically VCO available in IC form. The commonly used VCO ICs are NE by SE 566. It is 8-pin IC, which provides 2 output pins. With the help of that IC, simultaneously generates square wave and triangular waves outputs. The input voltage is also called as modulating input voltage. Practically, VCO available in IC form. The commonly used VCO ICs are NE by SE 566. It is 8-pin IC. Which provides 2 output pins. It is a feature is that simultaneously IC provides square and triangular wave outputs, which are the functions of input voltage. Its feature is that feature is that simultaneously IC provides square and triangular wave, outputs, which are the functions of the input voltage. Here is some important point related to voltage control oscillator. This is the pin diagram. Practically, VCO available in IC form. IC 566 VCO, NE by SC 566 VCO. First one is ground. First pin is ground. Second is not yet connected, not used. Third pin is the square wave output. Fourth pin is meant for triangular wave output. Fifth is modulating input, that is control voltage is applied to fifth pin. Externally applied components are resistance and capacitance. R1 is connected to sixth pin, C1 is connected to seventh pin, and V is the voltage, DC voltage is connected to eighth pin. Generally, IC 566 VCO is a 8 pins. The functions of 8 pins are like that. Next, block diagram. This is the block diagram of of VCO. Two types of waveforms generated, already explained, square wave and triangular waveform. Here important points are related to the frequency. The frequency of oscillations is determined by an external resistor. These are the frequency of oscillations. It is an oscillator circuit, no doubt. Generates two types of waveforms simultaneously, square waveform and triangular waveform. The frequency of oscillations can be controlled by this input voltage Vc. The frequency of oscillation is determined by an external resistor R1, capacitor C1, and the voltage Vc applied to control terminal. Important point here is related to block diagram. The frequency of oscillations. The frequency of oscillation. Frequency means we had some time period is there, F is equal to 1 by T. Some time period is there, F is equal to 1 by T. The frequency of oscillation is determined. The frequency of oscillation is determined by an external resistor R1. External resistor R1, comma, external capacitor, external capacitor C1, and the voltage and the voltage Vc applied to the control terminal. Applied to the control terminal. One more important point here is the triangular waveform is generated. This is the triangular waveform is generated by alternately charging the capacitor and discharging the capacitor by using current sources. The triangular wave is generated by alternately charging the external capacitor by one current source and then linearly discharging it by another current source. Here current source is called as constant current source and sink. Constant current source constant current source and sink and sink. First one, current source. Coming to that current source. This is the capacitor. The triangular wave is generated by alternately charging the triangular wave is generated by alternately charging the external capacitor by one current source and the linearly discharged and then linearly discharging it by another current source that is called as sink. Current sources means constant current source by sink. Here constant current source by constant current source by sink. Constant current source is used charging the capacitor linearly and discharging the capacitor through the sink only. The triangular wave is generated by alternately charging the external capacitor by one current source that is called as constant current source and the linearly discharging it by another current source that is called as sink. The charging and discharging levels are determined by Schmidt trigger action. The charging and the discharging levels are determined by another important point here is the charging and discharging levels are determined by Schmidt trigger action. Schmidt trigger action. Here important point is the capacitor C1 is linearly charged or discharged by constant current source and the sink. The charging current can be controlled by controlling the voltage Vc at 0.5 here. IC has current sources shown in the figure that are responsible for charging and discharging the external capacitor C1. The external resistance R1 and the DC input voltage decides the rate of charging and discharging. The charging and discharging levels are determined by the Schmidt trigger. These are some important points. The Schmidt trigger. Another important point here is a Schmidt trigger circuit. A Schmidt trigger circuit is used to switch the current sources. Constant current source and sink between charging and discharging. charging and discharging. Discharging the capacitor. And the triangular voltage developed across the capacitor and the triangular voltage or waveform voltage developed across the capacitor and a square wave from the Smith trigger and square wave and a square wave from the Smith trigger. Are provided as outputs through buffer amplifiers. Are provided as outputs. Are provided as outputs. Through buffer amplifier. Here explanation of this one is, first one is current source. Current source are two types, constant current source and a sink. Constant current source is used to linearly charge the capacitor C1 and the capacitor is linearly discharges it by another current source that is called as a sink. Mid trigger. The charging and discharging levels are determined by the Smith trigger. The charging and discharging levels are determined by the Smith trigger. Finally, the capacitor C1 is linearly charged or discharged by a constant current source and sink belongs to current sources. The charging current can be controlled by the controlling voltage, which is applied VC at pin 5. The external resistance R1 and the DC input voltage V. This is external resistance R1 and the DC input voltage decides the rate of charging and discharging. Another important point here is the external resistance. R1 and the DC input voltage V. DC input voltage V decide the rate of charging, and discharge. This is the rate of charging and discharging. This one is a theory related to block diagram of VCO. The charging and discharging of this capacitor with the help of a current source and control voltage and externally applied DC voltage and R1, external resistance R1 generates triangular waveform. This triangular waveform is obtained at a fourth pin of this IC through buffer amplifier. The output of the Smith trigger is also some feedback here, The output of the Smith trigger is connected to that current source for comparison purpose. The Smith trigger generates a square waveform. The square waveform is obtained at a third pin of that IC through buffer amplifier. This IC provides two waveforms through buffer amplifiers. This is the description of that block diagram of VCO. Next one, explanation, operation. Here operation. Here constant current source, modulating input voltage R1 and V. Here C1 buffer, Smith trigger circuit, inverter circuit is like these are some important components. Takes place inside this rectangular box or square box represents IC. These are the pin numbers 5, 6, 8, 3, 4, 1, 7 like that. One more important point here is the output voltage of the Smith trigger is designed to switch between V and 0.5 V. Here output of the Smith trigger. An important point is the output voltage, the output voltage of the Smith trigger is designed to switch to swing or switch between V and 0.5 V. V and 0.5. Here RA is equal to RB is equal to R. For RA is equal to RB is equal to R, the voltage at non-inverting terminal plus the voltage at non-inverting terminal swings between 0.5 volts and 0.5 V to 0.25 V. Next, if RA is equal to RB is equal to R in the positive feedback, this is the positive feedback because output is connected to non-inverting terminal of that op amp, non-inverting terminal of op amp. If RA is equal to RB in the positive feedback loop, this is the positive feedback loop. The voltage at the non-inverting input terminal of A2 swings from 0.5 to 0.25. Another important point in that operation, I will show how the voltage swings from 0.5 V to 0.25. For if RA is equal to RB is equal to R in the positive feedback loop, in the positive feedback loop, positive feedback means output of that Smith trigger is connected to non-inverting terminal of that op amp A2. That is the positive feedback loop. The voltage at a positive feedback loop, the voltage at the non-inverting input terminal, non-inverting input terminal of A2 swings from 0.5 V to 0.25. Here at the output of that, the output voltage of Smith trigger is designed to swing between V and 0.5 V. Here, the voltage at non-inverting terminal of A2 in the positive feedback loop is designed swings from 0.5 volts to 0.2 volts. Next one, operation. Next one here is operation. Here, first V volts is applied here. The output of the let the output of the Smith trigger is V volts. Output of the Smith trigger is V volts. Trigger is V volts. This V volt is also applied to constant current source. The V volts is applied to constant current source. At this point, in that feedback loop, the voltage at the non-inverting terminal of V2 is that is, let it be Vx. Find out Vx. Vx is equal to V into Vx with respect to ground. Vx with respect to ground. Vx is equal to total voltage applied to this loop is feedback loop is V into that voltage RB by RB plus RA. RB and RA is equal to R. Equal resistances. That is equal to V by 2. This is 0.5 V. This is 0.5 V. Here this V volts is also applied to constant current source. With the help of this control voltage, the capacitor is charged. The capacitor is charging through this buffer. That voltage charging voltage is applied to inverting terminal of the Smith trigger. The charging voltage is applied to inverting terminal of the Smith trigger. Here 0.5 volts is there. Whenever the capacitor voltage is reached to 0.5 volts, not exceed, not reach to V volts, 0.5 volts, because here 0.5 volts is there. Here the Smith trigger output swings from V to 0.5 V. V to 0.5 V. Because the Smith trigger, the output voltage of the Smith trigger is designed to swing between V and 0.5 V. This 0.5 V is also applied to constant current source. Here again 5 Vy is equal to 0.5 V into R by 2R. That is equal to 0.25 V. 0.25 V. If RA is equal to RB is equal to R in the positive feedback loop, the voltage at non-inverting terminals of A2 swings from initially 0.5 volts and later 0.2 volts. Here 0.25 volts is there here, but capacitor is charging. The capacitor is charging and reached to 0.2 volts. Again, the output of the Smith trigger switches to V volts. In that fashion, the loop is repeated, generates square wave and triangular wave. Charging and discharging of that capacitor is generates square wave, triangular wave, not square wave, triangular wave. Through that buffer, that waveform is available at fourth IC, this one. Here, Smith trigger output is a square waveform. Generally, here we use inverter. That inverter is a current source, produces a square waveform at the third pin of that IC. This is the explanation operation related to VCO. In the waveforms, output voltage at pin 4. This one is capacitor voltage. Here, Smith trigger. Smith trigger output. Initially, the Smith trigger is designed. The output of that switch trigger is switching between swings between two voltages V and 0.5 V. Initially, the Smith trigger voltage is V plus V. That V is applied to that constant current sources through feedback. With the help of that V, the capacitor is charged to here. The capacitor is charged to 0.5 volts. Why? Because 0.5 volts here Vx is equal to 0.5 volts. Here Vx is equal to 0.5 volts. Therefore, the capacitor is, voltage is reached to 0.5 volts. The capacitor is reached to 0.5 volts charging. Immediately the Smith trigger output is swings to 0.5 volts because the whenever the Smith trigger output is 0.5 volts, the capacitor is discharges up to 0.25 volts. The capacitor is discharges up to 0.25 volts. 0.25 volts. The capacitor is discharged up to 0.25 volts and 0.5 volts. Whenever capacitor is discharges to 0.25 volts here, compare these two voltages. Here it maintains 0.5 volts. These two voltages are equal. Again, the output of the Smith trigger is plus V volts like that. The capacitor is charges. The capacitor charges up to 0.5 volts. 0.5 volts. Maintains is like that. Whenever the capacitor voltage is reached to 0.5 volts, the Smith trigger output is changes to 0.5 volts. It constant one. At that instant, capacitor is discharges like that. The capacitor is discharges like that. Output at pin 3. At pin 3 is inverted. Square wave is generated. Square wave is generated at pin 3. Triangular wave is generated at pin 4. Like that. In this region, the capacitor is discharges. In this region, the capacitor is charging. Whenever the capacitor is charging reaches to 0.5 volts, the Smith trigger output is changed to another level that is called as 0.5 volts and maintains a constant one. During that constant period, the capacitor is discharges to 0.25 volts. Whenever that output of the Smith trigger is 0.5 volts, the voltage at the non-inverting terminal of op-amp A2 is 0.5 by 0.25. Therefore, the capacitor is discharged to 0.25. Whenever the capacitor is completely discharges, the Smith trigger output changes to again V volts. The same analysis is repeated. Finally, two types of waveforms are generated here. This one is charging and discharging. T is equal to 2 delta T. Charging and discharging at a constant rate. This one is delta T. This one is delta T. T is 2 delta T. T is 2 delta T. Next, derivation, frequency of oscillations derivation. Generally, the voltage on the capacitor changes from 0.25 volts to 0.5 volts. The voltage on the capacitor, changes from 0.25 volts to 0.5 volts. Therefore, the change in voltage delta V is equal to 0.5 volts minus 0.25. That is equal to 0.25 volts. 0.25 volts. We know that I is equal to C into change in voltage by delta T. The capacitor is charging with a constant source, that is charging rate and discharging rates are similar. Therefore, delta V by delta T is equal to I by C1. Here C1 is used here. Delta V is 0.25 volts by delta T is equal to I by C1. From this expression, delta T is equal to 0.25 VC1 by I. The time period of the triangular waveform is the time period of the triangular waveform T is equal to here T is equal to delta T plus delta T, 2 delta T, 2 delta T. Therefore, F is equal to 1 by 2 delta T, 1 by 2 into 0.25 V into C1, here I that is equal to I by 5 VC1. But I is equal to V minus DC voltage is applied and the control voltage VC by external resistance R1. External resistance is R1. Therefore, F naught is equal to 0.5. This one is 0.5. I is V minus control voltage VC by VC1. VC1 into here R1. I is V minus VC by R1 VC1. 1 by 0.5 is 2. 2 into the output, 2 into V minus VC by VC1, V into C1 into R1. Therefore, the output frequency of the VCO can be changed either by R1, C1, and the voltage VC at the modulating input terminal, that is control voltage. The output frequency of the VCO can be changed. Either by R1, C1, or the voltage VC at the modulating input terminal. With this, the analysis part is completed.